Section 1 Introduction. We're going to delve into the fascinating world of large language models, LLMs, that have been gaining a lot of attention in various fields, including production, research, and open source communities. These models have been significantly improved thanks to advancements in GPU technology and memory-efficient exact attention methods. However, there's another method that's been around for a while that's also effective for handling long contexts: retrieval. In simple terms, retrieval involves the LLMs reading only the relevant context retrieved from a standalone retriever. This method is much faster and easier to scale than LLMs when it comes to selecting relevant context. You can think of the retrieval-augmented decoder-only LLM as applying sparse attention over its long context window, where the sparsity pattern is determined by the standalone retriever. Any context that isn't retrieved is considered irrelevant and given zero attention weight. Despite the growing interest in long-context LLM research and the increased computational requirements, it's still unclear whether extending the context window of LLM provides higher accuracy than retrieval augmentation for tasks with informative queries. We're also interested in exploring whether we can combine the strengths of both methods to achieve even higher accuracies. To answer these questions, we conducted a comprehensive study and made the following contributions. 1. We carried out an extensive study using two state-of-the-art LLMs, a proprietary 43B pre-trained GPT and Llama 2 to 70B, on 7 downstream long context tasks. These tasks included single and multi-document question answering, QA, and query-based summarization. 2. We found that retrieval augmentation significantly improves the performance of 4K context LLMs. Interestingly, this simple retrieval-augmented baseline can perform comparably to 16K long context LLMs, while using much less computation. 3. We also found that the performance of long context LLMs, i.e., 16K or 32K, can still be improved by retrieval, especially for the larger Llama 2 to 70B. As a result, our best model, retrieval-augmented Llama 2 to 70B 32K RET, outperforms GPT 3.5 Turbo 16K and DaVinci 003 in terms of average score. It also significantly outperforms its non-retrieval Llama 2 to 70B 32K baseline, while being much faster at generation. In the following sections, we'll discuss related work, present our experimental setup, report our results, and conclude our paper. Over the past few years, pre-training large language models, LLMs, with long context windows has become a viable solution thanks to faster GPUs with more memory and memory-efficient exact attention. For example, the context window for pre-trained LLMs has been increased from 1024 of GPT-2, 2048 of GPT-3, 4096 of Llama 2, to 8192 of GPT-4. However, further extending the context window in pre-training can be challenging due to the quadratic time and memory complexities of exact attention, and the fact that most documents in the pre-training corpus are relatively short. Recently, researchers have started to extend the context window of LLMs with continued training or fine-tuning. For instance, long LLAMA was introduced by fine-tuning the 3B and 7B open LLAMA checkpoints with contrastive training on 8K context length. Landmark attention extends the context length of Llama 7B from 4K to 32K by introducing landmark tokens to represent blocks of the context and fine-tuning the attention to use landmark tokens for selecting relevant blocks. In this work, we applied the positional interpolation method to extend the 4K context window of a proprietary 43B pre-trained LLM and Llama 2 to 70B to 16K and 32K, as they both use rotary position embedding at pre-training. We focused on downstream task performance after instruction tuning. There are other studies showing the interplay between retrieval augmentation and long context LLM. Section summary. The recent development of faster GPUs and memory-efficient exact attention has led to advancements in long context large language models, LLMs. However, an alternative approach to handling long context is retrieval, where LLMs only read relevant context retrieved from a standalone retriever. In this study, we comprehensively explore the performance of retrieval-augmented LLMs and find that they can achieve comparable accuracy to LLMs with larger context windows, while requiring less computation. Additionally, we demonstrate that retrieval can further improve the performance of long context LLMs. Section 2.2 Efficient Attention Methods. In the past, various methods have been developed to address the computational challenges posed by the quadratic complexity of self-attention, especially when dealing with long contexts. These methods can be broadly categorized into 5 groups. 1. Sparse attention mechanisms that use predefined sparsity patterns. 2. Recurrence-based methods. 3. Low-rank projection attention. 4. Memory-based mechanisms. 5. Methods based on similarity and clustering. While these methods can be effective in specific domains due to their inductive bias, like predefined sparsity, they may not always improve the overall quality of large language model (LLM) training. Recently, a method called flash attention has been introduced to speed up attention computation by managing reads and writes between different levels of GPU memory. This method is particularly useful for handling longer sequences. Retrieval has been used in language models for many years to enhance various aspects such as perplexity, factual accuracy, downstream task accuracy, and in-context learning capability. When combined with a standalone retriever, retrieval-augmented LLMs have proven effective for answering questions within long documents and in open domains. There have been attempts to integrate LLMs and retrievers into a single model to create an end-to-end solution. However, most of these studies have focused on LLMs with around 10 billion parameters. In this study, we focus on decoder-only LLMs with 43 billion and 70 billion parameters trained on trillions of tokens, as these large-scale LLMs have a strong ability to incorporate context after instruction tuning. While preparing this manuscript, we noticed a concurrent study that also explores the impact of retrieval on long-context LLMs, including models like GPT 3.5 Turbo 16K, Llama 2-7B Chat 4K, and Chat GLM 2-6B 32K. However, their findings differ from ours. They found that retrieval was only beneficial for the Llama 2-7B Chat 4K model with a 4K context window, but not for the long context models like GPT 3.5 Turbo 16K and Chat GLM 2-6B 32K. We believe this discrepancy may be due to the challenges of conducting controlled experiments using black box APIs and the relatively small size of the LLMs used in their study, which limits their ability to incorporate context through retrieval. Our conclusions are based on much larger LLMs. In fact, our best long context model, Llama 2-70B 32K, performs as well as ChatGPT 3.5 and can still be improved with retrieval. In our experimental setup, we focus on comparing the ability of large language models to integrate long context information for generative question answering or summarization tasks, either through retrieval or the LLM's own self-attention mechanism. Unlike most existing studies that focus on relatively small models, like 3 billion or 7 billion parameters, we explore models larger than 40 billion parameters after instruction tuning. We experimented with 2 pre-trained GPT models, a proprietary NeMo GPT-43B and Llama 2-70B. GPT-43B is a 43 billion parameter model trained with 1.1 trillion tokens, 70% of which are English and the remaining 30% are multilingual and code data. It was trained using a variety of English sources, including Common Crawl Web Archive, Wikipedia, Reddit, Books, Gutenberg, Archive, Stack Exchange, PubMed, and others. It has 48 layers with a hidden dimension of 8,192 and was trained with a sequence length of 4,096 and rope embeddings. Llama 2-70B is a publicly available 70 billion parameter GPT model trained on 2 trillion tokens, about 90% of which are English. It has 80 layers with a hidden dimension of 8,192 and a context window size of 4,096. It was also trained with rope embeddings. In this study, we used 7 datasets ranging from single-document question answering, multi-document question answering, to query-based summarization for our zero-shot evaluations. These datasets include QM-Sum, Casper, Narrative QA, Quality, Musique, Hotpot QA, and Multi-Field QAN. Our evaluation datasets have a wide range of average document lengths, from 4.9K, QASP, to 84K, NQA. For the baseline model without retrieval, we truncate the document to fit into the input sequence length. We report the geometric mean of Rouge scores for QM, the exact matching score for QLTY, and F1 scores for the remaining 5 datasets QASP, NQA, MSQ, HQA, and MFQA. Section Summary. Efficient attention methods have been developed to address the computational bottleneck of self-attention in long context models, including sparse attention mechanisms, recurrence-based methods, low-rank projection attention, memory-based mechanisms, and similarity and clustering-based methods. Retrieval-augmented language models have been widely used to improve perplexity, factual accuracy, downstream task accuracy, and in-context learning capability, with various approaches such as integrating retrieval at inference, fine-tuning, and pre-training. However, most previous works focused on smaller models, while this study focuses on larger decoder-only language models with 43B and 70B parameters, which exhibit strong zero-shot capability to incorporate context after instruction tuning. Section 3.3 Context Window Extension. We've expanded the context window length using a method called position interpolation, which is simple and effective for rope embeddings. We've increased the 4K context window to 16K for GPT-4.3b, and for Llama 2 to 70B, we've extended it to both 16K and 32K. We've fine-tuned both of these language models on the PILE dataset, using a batch size of 128 and a constant learning rate of 5e6 to adjust the position embeddings. For the retrieval process, we experimented with 3 different retrievers: Dragon, Contriever, and OpenAI Embedding 5. Dragon is a dual encoder model that has achieved top results on both supervised and zero-shot information retrieval benchmarks. Contriever, which is widely used, employs a simple contrastive learning framework to pre-train models for information retrieval. It was trained without supervision and achieved competitive results with BM25 for R at 100 on the BEIR benchmark. For the OpenAI embedding model, we used the latest version, Text Embedding ADA-002, as recommended by OpenAI. It can handle a maximum of 8,191 input tokens for one sequence and produces an output vector of 1,536 dimensions. We then calculated the cosine similarities between the questions and a list of contexts for retrieval ranking. To use these retrievers, we first divided each context document into 300-word chunks. We then encoded both the questions and all chunks independently with the corresponding encoders. The most relevant n chunks, ranked by the dot product of the question embedding and chunk embedding, were then concatenated together in order of relevance to form the context of the prompt for generation. We also performed instruction tuning to train the pre-trained language models to follow instructions for question answering or text summarization. We constructed a blend of instruction tuning datasets consisting of 102K training samples from various sources to adapt both GPT-4.3b and Llama 2 to 70b to follow instructions. We used a specific format to support multi-turn dialogue training and fine-tuned the language model by taking the loss only on the answer part with a batch size of 128 and a learning rate of 5e6 for 1,000 steps. In our results, we found that baseline models without retrieval of 4K sequence length performed the worst for both GPT-4.3b and Llama 2 to 70b. This is because the minimum average sequence length of all 7 tasks exceeds 4,096, the context window of the foundation models, and therefore valuable texts get truncated randomly. As a result, retrieval is especially helpful for 4K language models. We also observed that Hotpot QA, HQA, especially favors long sequence models as the score improves significantly when the sequence length increases from 4K to 16K. This is because Hotpot QA is a multi-hop dataset where the questions are not hard to answer but all intermediate hops are necessary to get the correct answer. Therefore, long contexts are beneficial to increase the recall of incorporating all intermediate hops. Interestingly, the retrieval-augmented long context language model, e.g., 16K and 32K, can obtain better results than retrieval-augmented 4K context language model, even they are fed with the same top 5 chunks of evidence. We hypothesize this interesting observation is related to the lost in the middle phenomenon, where the language models are better at utilizing relevant information that occurs at the beginning or end of its input context window. We found that retrieval can significantly improve the performance of both GPT-4.3b and Llama 2 to 70b regardless of their context window size. For example, our best retrieval-augmented Llama 2 to 70b 32K RET outperforms its baseline without retrieval by a margin. We think the major reason for such different conclusion is that uses much smaller language model with 6B and 7B parameters, which usually has relatively worse zero-shot capability to incorporate the retrieved chunked context. In contrast, the larger instruction-tuned language models like Llama 2 to 70B has much stronger zero-shot capability to incorporate retrieved evidence. This observation is becoming more clear when one compares the gain of retrieval augmentation between GPT-4.3b and Llama 2 to 70b, where Llama 2 to 70b enjoys larger benefit of incorporating context through retrieval. Section Summary. In this section, the authors discuss the extension of the context window length for rope embeddings, where they extend the 4K context window to 16K for GPT-4.3b and 16K and 32K for Llama 2 to 70b. They also describe the three retrievers used in their experiments: Dragon, Contriever, and OpenAI embedding. They chunk each context document with 300 words and encode both the questions and chunks independently with corresponding encoders for retrieval ranking. Section 4.2 Comparing to OpenAI models. In this section, we're going to delve into how our top-performing model, Llama 2 to 70B 32K with retrieval, stacks up against other models from OpenAI, such as GPT 3.5 Turbo 4K, GPT 3.5 Turbo 16K, and DaVinci 003. We tested these models on 7 different datasets, including QM-Sum, Casper, Narrative QA, and Quality. The test set from the Zero Scrolls leaderboard was used for these 4 datasets, as it already had scores for GPT 3.5 Turbo, 4K, and DaVinci 003. Our findings showed that Llama 2 to 70B 32K with retrieval outperformed GPT 3.5 Turbo 16K in terms of average accuracy across all 7 datasets. It also surpassed DaVinci 003, which has 175 billion parameters, in average performance across 4 tasks. This suggests that our Llama 2 to 70B 32K model with retrieval is a strong contender for tasks involving long contexts, and our conclusions are based on the latest, cutting-edge results. Next, we wanted to explore how different retrievers affect the performance of Llama 2 to 70B. We compared Dragon, Contriever, and OpenAI embeddings on top of Llama 2 to 70B 4K and Llama 2 to 70B 32K. Our results confirmed that retrieval can enhance the performance of both short and long context language models, regardless of the retriever used. Interestingly, we found that publicly available retrievers often outperform the proprietary OpenAI embeddings. We also investigated the effect of increasing the number of retrieved chunks in the context. We expanded the number of retrieved chunks from 5 to 20 using the Dragon retriever. Our findings showed that the best average results were achieved with either the top 5 or top 10 chunks. Even though up to 20 chunks could still fit into the 16K and 32K context window, adding more chunks didn't improve performance and sometimes even hindered it. We think this could be due to the model getting lost in the middle, or being distracted by irrelevant information, but this requires further research.